Okay, so as I said at the end of the last video, our next topic is the mean and the median of density curves. So here are three density curves, nearly identical to the ones from the last video. And what I've done in them is I have drawn in where the mean and the median would be located in each of them. So if you notice in the top left of the slide, we've got a left skewed density curve, and its mean is slightly to the left of the median of that curve. And in the density curve that we have on the top right of the slide, we've got a skewed right curve, and its mean is slightly to the right of its median. And then finally, in the density curve that is symmetric, the mean and the median are going to be the same. And that's something that you should always remember. If you have a symmetric density curve, the mean and the median are going to have the same value. Now, why in the world is this? Really what you need to understand is that the more symmetric a density curve is, the closer together the mean and the median is. So, of course, the inverse of that would be that the more skewed a density curve is, the farther apart the mean and the median will be. So here's how your book describes or explains what the mean and the median of a density curve are. The mean you should think of as the balance point. In your book, they've got some cute little diagrams on page 127 of what they're talking about there. So imagine that a density curve is like a seesaw. I'm not enough of an artist to draw this for you, but again, imagine your density curve is like a seesaw, and the mean is going to be that point where your density curve would balance evenly on both ends. The median is the point in your density curve where you're going to have an equal area on either side. Now this one's probably a little bit easier to understand or to visualize. We said in the last lesson that in order for a curve to be considered a density curve, it has to have an area underneath it of exactly 1. So let's say we've got our roughly symmetric density curve here. If it's roughly symmetric, we know that the mean and the median will be the same point, and in fact they'll be right down the center. So here's our median for this particular curve. Now the equal areas point, all that means is that because we know the area underneath the curve is equal to 1, then I hope you know that half of 1 is 1/2. So that means that we should have an area of 0.5 on, oops, there's the decimal, an area of 0.5 on one side of our median underneath the curve, and we should have exactly the same thing, an area of 0.5 on the other side of the median underneath the curve. There is one little bit that you need to be aware of. Now I mentioned in the last lesson that this concept of a density curve is sort of an idealized concept. Density curves don't actually, no perfect density curve is ever going to be created out of a set of data. Data is invariably imperfect. But we've kind of got this sort of idealized goal of a density curve that we hope our data will reach. So to differentiate between the mean and the standard deviation of a density curve, we have to have some special notation. Up to this point, when we're talking about mean, we've only been talking about the mean or the average of a set of data, and we've been using x bar to represent that. That notation is not going to change. We're still using x bar to represent the average of our data set. But if we're talking about the mean of a density curve, we don't want to call it x bar because that would be misleading. X bar is based on exact data. The mean of a density curve, again, because that's sort of an idealized concept, we're going to call that mu. That's a Greek letter, and it looks like that symbol that I just drew. It looks like a letter U, except for one tail is long and a little bit curled off to the side. And then same way with the standard deviation. We've been using S to describe the standard deviation of our data sets, and that's not going to change, except that now when we talk about the standard deviation of a density curve, we can't use S, we need a new symbol, And this is another Greek letter. It's the lowercase sigma, which I think I've drawn for you already. But it looks like an O with a funny little hat off to the side. So here's how I draw mine. That's my version of sigma, but as long as you can draw something somewhat similar, we should all be good.